Okay, so good morning, and we start the study of real gases. Okay, so we have already seen the ideal gas, and for instance, derived the equation of state. In fact, we derived the full free energy as well, and that was just PV equal to N kb times T. Okay, so the statement here is that an ideal gas does not include interactions between the particles. Okay, so that is, we know that that's the idealization, and so that's the issue. But there's another sense in which it's not real. An ideal gas will remain a gas at all temperatures. Okay, and however, what we call a real gas can will have a, you know, it will have a liquid to gas or vapor transition, but there can be also solid to liquid, and there are situations where you can go straight from solid to. So these are the things that a real gas or a real substance would do. Okay, so
Such is it because certain dust doesn't have any interactions.
so that's a straight answer to that. Yes, that. Okay, so now the question is, what are the kind of interactions that we would need, etc. Okay, so which would so we want general properties rather than details. Okay, for each gas, of course, there are specific details, each material, etc. So what kind of interparticle attraction, a potential will we need? Okay, and so the answer is actually there should be short range repulsion. Okay, so they won't come like close to each other. So for one example of one simple way of incorporating short range repulsion is to say that, particles have some finite size, so they cannot get closer than something. So it's like saying there's some infinite potential. So if the radius is a, so the separation can be 2a only, right? So that's like saying the potential is infinity, and so they cannot. Okay, short range repulsion and long range. Weak is enough. I won't quantify what is weak, but okay, weak, long range attraction. Okay, so these are the general properties that that you need to for real gases, and of course there are several what is it called, the potentials, candidate, I mean model potentials with such behavior. Okay, and so one example is the one, it's called the van der Waals potential, I think, right? So don't know. This 1 by r power 6 and 1 by r power 12, right? What is that potential called? You would have read it and studied it somewhere, right? What is it called? I can't hear. Lennard-Jones potential. That's easy. I'm not very good with names. Yeah. So it's called the Lennard-Jones. So that will be some V. So let's assume it's some radially symmetric thing. So it would be like some constant r power 6. Okay, and let's say A and B are constants, B r power 12. And now I want you to help me fix the sign. So first question is, what dominates for large R? Which term? R power 6. Okay. And what dominates for small r?
1 by r power 12.
Okay. So we want, so I'm going to fix the thing. So we want weak long range attraction. So long range means R large. So I should put a minus sign here. Okay. And repulsion means positive sign, right? So that's okay. So A and B are positive constants. Okay. I'll give another one. I'll draw a graph for it. This doesn't have a name or anything. So let's say there is some size A here. So it's infinity till here. And we want it to be weakly attractive. So some small. Let's use a different color for the potential. Okay, so this is the potential, for instance, which has the same property. Yes, I have to have it somewhat positive, so that's all. Okay, so this is the kind of potentials that is. There are many more examples, but you can see that these kind of things will achieve what we need. And so
why r power 6 and 12?
Okay, so the thing is that the dominant, I used to know this argument, so let's just do it and see, at least for R power, I think R power 6. So I think it's dipole interactions or something. You can work out those things. So if you look at the potential for charged particle, it's 1 by R, and then if you take a dipole, it falls off as 1 by R square.
Yes, sir. You will never get 6 and 12, right?
Huh? So there is some logic. I mean, there's some logic. I mean, I don't know exactly, but this is not the only potential. There are many other candidates, but this is very common. But there is some. I do remember some logic behind R power 6. 12, I don't remember, but R power 6 for sure. So we can look it up. Why don't you also look it up? And there is some reasoning behind this. I don't remember at this point. Okay.
Yes, sir.
Okay, but what I'm saying here is just that at least we can make signs of the sense of the two terms. Okay, we are able to fix those things. Okay, but you won't be putting 1 by R. Okay, because most things are neutral. Okay, so it has to be faster than 1 by R. It should fall to 0 faster than 1 by R. Okay, so
what is the criteria to decide whether R is small or large? I mean, what is the range of R? Should we take A and B?
Range of R here, R belongs to 0 to infinity.
For long range, bigger values of R we should take here like that. I mean, what range of R should be considered for a small and what range should be considered?
No, I mean this it's a potential for all R. I mean that's it. I mean you can plot this and you will see. So this will V of R here. This will have some behavior like this. My memory is right, something like this with some minimum. Okay.
Okay.
So okay. So we need to put this in. So of course, the way would be way ahead would be to compute the canonical partition function. Okay, which is something like this. Z would be some integral d3n p d3n x by h power 3n. Okay, and possibly some 1 by n factorial here to take care of it. E power minus beta times h, where h is just the free particle thing for momentum thing, minus plus v of r. So summation I less than j v of rij, where rij is xi minus xj. Okay, so we can go ahead and we can do this computation. Obviously, we cannot do this integral, but there is some part of it we can try to do, and there are approximate methods. Okay, so we will do this computation later. Okay, later. But before that, I want to discuss the phase diagram of real. Okay, so before that, okay, let us discuss the phase diagram of a real material, real gas. Okay, and so let me start doing that. And so first, let's draw axes. Terrible. This looks better. Looks like 90 degrees. So the phase diagram is usually given pressure versus temperature. Okay, and the structure is as follows. So that's a special point from which let me change colors. Okay, so there are three phases: solid, liquid, and gas. And so now you got to help me. Which one? What will come here?
Gas.
Yeah. Thank you. What will come here?
Liquid.
Thank you. And what will come here?
Sorry.
Okay. Thank you. So perfect. Okay. So first, let's look at the so there are some special values here, okay, of pressure and this thing. And so let's look at the liquid gas line. So this is the yellow line here is the liquid gas coexistence curve, right? Okay, and so this is a line of first order phase transitions. Okay, and this object that I've circled at that point, that becomes a second order one. Okay, so that Big circle is a second order phase transition. Okay, so what it says is that as you go in this direction, the latent heat, which we know, okay, the latent heat goes to zero. Okay, at this point. Okay, is this clear? So I'm just giving you a schematic, and so we'll call. So this is similar to what happened in the case of the magnetic analog, where so it was the para and the ferro transition, and if you remember, at exactly at t equal to tc, at the critical point, it was second order phase transition. But once you turned on B, then those you got a line of first order phase transitions, right? So it's in that sense similar to that. Okay, which separated the two ferro phases, actually, not para and ferro. Okay. Okay, so just remember that. So we have this, and this is called the critical point. Okay, is this clear? What we are? I've just discussed one line, out here. Okay, so are there any questions and comments?
Sir, we can still get the critical point even with the magnetic field on, right?
Is that right? Yeah. Okay. So let us, we'll discuss that in a moment. Okay. So, okay. So by that, what do you mean?
So, like you just said, like turning on the magnetic field will make us, like.
But it was, so when we turned on the magnetic field and when we start reducing, right, when it comes to zero, so what we saw was a jump, right? I mean, so what is it you want? How will you tune it? What do you want to keep fixed and what do you want to vary? Okay, so let's just postpone that. We won't discuss it now. Let's just at least understand this phase diagram. Okay? Okay. So next, let's look at this line. Okay. So this is the solid liquid phase transition. Okay. And here there is here what is happening is that these again will be a series of first order phase transitions, but it will be solid to liquid. Okay, again something which we know from ice to water transition. We know that, right? So that there is some latent heat that you need to give. Okay, so but this will go up to infinity, and here is the point which I want to make. Solid, liquid is isotropic. There's no preferred direction in a liquid. Okay, same thing is true with the gas, right? Inside a gas is isotropic, but a solid is not, right? A crystal is not isotropic because there are directions, right? Special directions. Each direction looks different, right? So there is a sense in which solids are totally ordered in terms of spatial order, but liquid and gas, both of them are isotropic. Okay, and so actually here you can do one thing, which is just I'll draw something, and then so we can peacefully go from liquid phase to the gas phase or vice versa by just going around the critical point. You wouldn't notice it. Okay, so somewhere out here, what will you call? I mean, is it liquid or gas? No, you just call it fluid. Okay, so liquids and gases, there is some difference. Only in the neighborhood of this yellow line, there you can. But you can smoothly go around this the critical point to go from gas to liquid. There will be no latent heat, nothing. You will not see any of those things because you have bypassed this thing. But you can see you have to do some special tuning. You have to make P and T. You have to vary it in some particular way to make it work. Okay, so out here we'll just call it fluid. Okay. And one more thing, so you cannot, so you can ask, sir, is it possible for the solid line to be such that you actually have a critical point there? And the answer is no. Okay, and this is a symmetry argument in the sense, like I just told you, solids and liquids, they are not. There's no way you can mistake a solid from a liquid, if you wish. Okay, so that's like intuitive reason why. This will this dotted line goes up to infinity. Okay, there will always be some latent heat. Something there will be. It will remain a first order transition. Okay, so same thing happens. So here, this curve is that if you keep T fixed, then you keep changing. If you keep P fixed, then you go like this. You go directly from solid to gas. Okay, so what is this curve? What is that thing called when a solid becomes a gas?
Sublimation.
Right. So this curve is called the sublimation line. Okay, so curve or whatever. This is the curve of sublimation. I don't know. Is it correct to call it sublimation curve? I'll call it. Okay. Again, that will be a set of first order transitions. But this central point, which I have marked here, okay. So what is this point called? Triple point, right? Call that triple point. Okay. At this point, we have three phases coexisting: solid, liquid, and gas. Okay, so triple point is special. Okay, and that is so this is the maximum possible. Okay, why am I saying that? Can we have four phases? So it turns out, ice has, many different phases. So the diagram which I'm showing you here is actually not good for ice, because ice has many solid phases. Okay, so many. So you might think, can we have four phases coexist? That's what I'm asking. So in water ice, yes.
Can you explain what you mean by ice has many phases?
Many different crystalline configurations, many things it has. So it's a very complex diagram. It has multiple solid phases, not just what you know. It depends on pressure, it depends on these things. So the phase diagram is much richer than what I have drawn. I'll share something with you. Okay. So I don't know the precise details of all the phases, but I'm just saying that there are many. You must have also read about snowflakes being many different kinds of snowflakes and stuff like that. A related point. Okay, so this is just the maximum possible. And how do you prove this? It's just counting. Okay, so the point is that so here we have two control parameters. We'll call it P and T are the control variables, or the way I have drawn it, or what did we call it? We call it the state variables. Independent state variables. Okay, so now you can see that what you will need is if you want to have in a plane, if you want to have coexistence of one phase, you'll have to draw one line. Okay, and then if you want to have a second phase also coexist, you have to draw something like. Okay, so something like this. So this picture. Okay, yeah, good enough. This is good enough. And so this kind of tells you that if you do dimensionality counting, you will require many things to synchronize, so that won't happen. And so there's something in thermodynamics called the Gibbs phase rule, okay, which is just some trivial dimensionality counting, okay, it is some. Excuse me, 1 second. Why are you disturbing me? Class left. Okay. Okay, so this is the best. So coming back to this, so I think so according to this, you can have only two phases, and so please look this up. Check if what I'm saying is true. That a max of okay. Don't
Hello,
trust me.
sir. Your mic is muted.
Oh, thank you. Okay, so what I'm just saying that this Gibbs phase rule, look it up and check that if my claim that there are a max of 3 phases that can coexist in this system, this is correct. It's just counting of how many curves how many conditions you need to have intersections work and stuff like that. That's all. Okay, so this picture, I mean, so if this is some phase 1 and phase 2, then this would and this would be this on this side. If it is 1, this should become 3 or something like that. Anyway, check. Maybe this is 3, 4. I don't know. Okay, check this. I think 3 is correct, but okay. So please look up. So read up on. So you might have learned this in chemistry. Usually this is done in chemistry, and chemistry is great. They always convert everything into some rule and this thing, but it is just some simple dimension counting. Okay, so now, yeah, so there is a well-known model for a real gas. Okay, and that's the van der Waals equation of state. One second, I just want to get the definition right. Yeah. So all of you have seen this. Okay, so it has two parameters. A and B. Okay, so exercise So what you do here is that plot. So first thing is plot P versus V. Okay, for different values of temperature. Okay, so of course you have to do some work to convert things into so instead of doing P versus capital V, it's better to do P versus little v, which is V by N. Okay, you can do that. Okay, so you can plot this, and what will happen is that this equation. Okay, so I'm just saying this thing, but we will see that there is a critical temperature. Okay, Tc, below which the PV curve changes shape. Okay, so let me show what happens. So let's look at, okay, so T versus V, right? So it's something like this, PV equal to constant. It looks like something like this. Okay, so if you look at this thing, there is some property out here. Let's compute, say, dP by dV. This is for fixed T. What is its sign?
Negative, sir.
It's always negative. Okay, so this has some physical meaning, and so first, if you remember, this is so P is in equivalently. If you are working in the canonical ensemble, where we're working with the Helmholtz free energy, this would be proportional. This will be some condition on d square m by dv square on the second derivative. So this should be related to stability. Okay, so what is the condition? Okay, so the condition for stability is some sign for the second derivative is that the compressibility okay, which is defined by what is it? Kappa is minus V, I think dP by dV. One second, let me look up the definition. I am not very good at some of these things. See, I got it all wrong. The inverse of it. Okay. And so compressibility should be greater than 0. That's the same condition as here. Okay. So the point here is, so let's, so on the van der Waals okay, one can see that at that critical temperature T equal to Tc, dP by dV will be 0. Okay, so in terms of okay, so this is what you should see. So it's like the start of okay, so how do you, so we can turn it around and this thing, and for T greater than Tc, rather T less than Tc, we will start seeing things like d square P by dP by dV was less than 0, right, you can start getting 0 or kappa B negative. Okay, so we start seeing that there is a instability. Okay, so maybe this is an exercise for you to do. So I should show you what would be the curve, right? So this is for high temperatures, so T greater than Tc. It will look like the ideal gas. Okay, so at high temperatures, the real gas will also behave more or less like this. Okay, so you need to, how do you go about plotting it? That is a exercise for you, that you plot these things. Okay, but so this exercise here is determine Tc. Okay, so you can do that, and so let me just do one more plot. Okay, so let's do the plot now for T less than Tc. Okay, so it will look something like this. This is V and this is P. Okay, so you can see that. So now let's look at the region. So let's just label things. So let's say that this point is A, this point is B, this point is C, this point is D, and this point is E. Okay, so now question to you is, where do we have the wrong sign of dP by dV, in which segment or whatever?
AB and DE. E and DE.
Yeah. What? Repeat.
Sir, AB and from DE, the DE part.
That's the correct sign, no? We want dP by dV to be negative, right? So it's B to D. Okay. So this is the unstable region, because compressibility is negative, so it's unstable. And remember, it's like in the presence of B also, when we looked at the magnetization, we saw that there were regions where there were, you could, the analog of BD where, the signs were wrong. Okay. So this is similar to that. Actually, the analogy can be made very, very perfect. And so it turns out that at high pressures, so what will happen? So now the question is, what is the phase? So what do the interpretations for points A and E? So the idea here is that there will be a phase transition. So the DE part is one phase, AB part is another phase, and then we need to figure out what actually, at least A and E will be two different phases. So the question to you is, which is the phase for liquid and which is the phase for gas? A and E. This is not a trick question.
So D must be gas, right?
E. Don't talk about D. Is like near the instable thing. So E is all I must. E. So E is gas, and A will be liquid. Okay. And so now it comes down to, how do we handle this region? Okay. So question is, okay. And so to do this, the answer is kind of Answer 1 is that we need to identify the precise the stable configurations. Okay, and so how would we do that? So for this, we need to compute the corresponding state function and impose the stability conditions. Okay, so it looks very, very complicated, but roughly what will happen is that, so first thing is, what is the state function? So if you remember, f for this gas would be a function of T and V, right? But the phase diagram that we drew has P and T. So what is it? So this is the Helmholtz free energy. So what is it? What is the appropriate free energy for that setup? Where P and T are the.
So we have P and V, right?
T and V, and P and T. So if I wanted to discuss this kind of phase diagram, so my control variables are P and T. So question to you is, what is the free energy of interest? So P, see here, a correct way of saying it is T and V are the state variables, right? T and V are the state variables. So we have to do a Legendre transform, right?
Yes.
Okay. And what is the pairing? Which is the pair of V? What is paired up with V? Or the variable conjugate to V?
Pressure.
Pressure, right? So then you get, I think it's called G, right? Gibbs free energy or something like that, right? So that's what you get. Okay. So what you do is you compute G for both phases. Okay, and pick the, say, minimization, okay, lower one. This looks pretty complicated, but we can do this. Okay, at least this can be done. Okay, and we will do this. Okay, so it looks complicated, but we can do it. But there is answer 2, which is a geometric by Maxwell, called the Maxwell tie construction, Maxwell's tie line construction. Okay, which says something like this. Okay, so the match, he says, so this is P versus V. It says draw a horizontal line like this, such that these two areas are equal. Okay, and this yellow straight line is the Maxwell tie line. Okay, so so question is, can we derive something like this? Okay, so this is what he said, draw this line. And so according to him, you come here, okay, and so what you have is a liquid here, and then at this point there is a discontinuity, okay, and this, so you see that we also know that and this is so this is liquid and this is gas. Okay, and so there is a jump, and we know that the specific volumes, if you wish, of liquid and gas are not the same. So there's a discontinuity, and you jump here, and this is like, and you come out here. So if you, of course, you can ask, but sir, what will happen if I'm somewhere here, a point like this? Okay, we will answer these questions. We will. I'm just showing you these things, and we will sit down in next few lectures. We will try to derive various things like this. Okay, so is this clear what I'm saying? So I'm just giving you a heuristic formula. Okay, so this line is where, in some sense, both phases can coexist. So if you started out with some liquid phase, and let's say you started slowly, you started doing something, started lowering, changing the parameters. Okay, you could let's say you started lowering, reducing pressure, so you start coming down here, and then you can ask what will happen. So what you'll find is that some fraction of the liquid will become gas, so that so you can get points like this. So a point like this is really saying that there's a mixture, both liquid and gas will coexist. But once you come to this region, then that region is pure gas. Okay, is this clear? Okay, so of course, answer 1 is kind of cleaner. Okay, so I'll finish here today with a simple question: does the Maxwell tie line construction follow from A1, the first answer? Okay, so what we're going to do next is to compute the partition function. For a real gas. Okay, that means we put in with interparticle potential. Of course, we cannot. Okay, this is not done exactly. There's an expansion. One computes this as a series, and we will look at the first non-trivial correction. Okay, and then connect this up. Connect this computation and provide formulae for A and B of the VDW gas. Okay, in terms of the potential. Okay, and then what we can do is compute the free energy for a VDW gas and implement answer A1, see what we get. Okay, and then last part is to obtain critical exponents. Near the critical point. Okay, so this will take around 2 to 3 lectures, not a lot. Okay, so is this clear what we are going to do in dual gases? Today's lecture was kind of overview, showing these pictures, but I want to ask you, how many of you have seen the Maxwell tie line construction? Has anybody seen this?
No, sir.
No, you haven't done course in thermodynamics because it's standard thermodynamic stuff. Doesn't matter if you haven't done it because we will see it. Okay. So no one, no, not one person in this whole class. Okay, so I'm done and I'll pause for questions.